When we look out into the night sky, we see a universe of brilliant light set against a backdrop of profound darkness. For most of human history, we saw only chaos. But over the last century, we've discovered that the universe has a structure. It's not a random scattering of stars and galaxies. It's an intricate, beautiful, and colossal network, a cosmic web. On the grandest scales, galaxies are arranged into unimaginably long, interconnected filaments and dense, bustling clusters. These brilliant threads of matter surround vast, dark, and almost empty regions of space, known as voids. Think of it like a sponge, where the sponge material is the galaxy filaments, and the holes are the cosmic voids. This is the normal, expected architecture of the cosmos. But in one direction, in a patch of sky that falls within the constellation of Eridanus, the river, astronomers have found something else entirely. It's not just a normal void. It's a hole in the very fabric of reality, a place that is colder and emptier than it has any right to be. It is a region of space so colossally empty and so unnervingly cold that it directly challenges our standard and otherwise wildly successful model of the universe. It's a supervoid measuring an almost incomprehensible 1.8 billion light-years across, and according to our best science, it simply shouldn't exist. This is the story of the CMB cold spot, a profound and chilling anomaly that could either be an incredible statistical fluke or the first hint of an entirely new kind of physics, perhaps even the first glimpse of a reality beyond our own universe, the baby picture of the universe. To understand why this cold spot is such a monumental problem, we have to travel back in time, all the way back to the very first light the universe ever produced. We have to look at our universe's baby picture, the cosmic microwave background, or CMB. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were trying to use a large horn antenna for their research, but they were stumped by a persistent, annoying hiss of static. It was a faint background noise that was the same no matter where they pointed their antenna. After ruling out every possible source of interference, including famously evicting a pair of pigeons that were nesting in the antenna, they came to a stunning conclusion. The noise was coming from space itself. They had accidentally discovered the afterglow of the Big Bang. The CMB is the oldest light in the universe. In the very early cosmos, for the first 380,000 years, the universe was an incredibly hot, dense, and opaque fog of plasma. Light couldn't travel freely. Photons were constantly being scattered by free-roaming electrons. But as the universe expanded, it cooled. At the 380,000-year mark, it reached a critical temperature where protons and electrons could finally combine to form the first stable hydrogen atoms. This event, known as recombination, cleared the fog. The universe suddenly became transparent, and the light that was present at that moment was finally set free to travel across the cosmos unimpeded. For the past 13.8 billion years, that ancient light has been traveling, its wavelength stretched by the continuous expansion of space from a brilliant, hot glow into the cold, faint microwave radiation that Penzias and Wilson detected. When we create a map of the CMB, we are literally looking at a snapshot of the infant universe. It is the most important single piece of data in all of cosmology, and its most important feature is its incredible uniformity. The temperature of the CMB is almost perfectly the same in every direction we look, a frigid 2.725 degrees above absolute zero. This observation is the bedrock of what's known as the cosmological principle, the fundamental assumption that on the largest scales, the universe is homogeneous. It has the same properties everywhere, and isotropic. It looks the same in every direction. But the key word here is almost. If the universe had been perfectly uniform at this early stage, gravity would have had nothing to act upon, and no structures like galaxies or stars would have ever formed. Thankfully, it wasn't perfect. Embedded in this ancient light are incredibly tiny temperature variations, or anisotropies. Our standard model of cosmology, known as the lambda cold dark matter, lambda CDM model, has been spectacularly successful at explaining the universe based on these principles. It makes very precise predictions about the pattern and size of these temperature fluctuations in the CMB. The model says that these fluctuations should be Gaussian, That is, they should be completely random, like the static on an old analog TV screen. There should be a certain average size for the hot and cold spots, but there should be no discernible patterns or structures. Crucially, the model also predicts a limit on how large any single coherent hot or cold spot can possibly be. And this is where our story truly begins, because in the constellation of Eridanus, there is a cold spot that breaks this rule. A hole in the heavens. For decades after its discovery, our view of the cosmic microwave background was blurry. We knew it was there, but our instruments lacked the resolution to map its tiny fluctuations in great detail. That all changed in 2001 with the launch of NASA's Wilkinson Microwave Anisotropy Probe, or WMAP. WMAP's mission was to create the first high-resolution, full-sky map of the CMB, to move from a blurry photograph to a sharp, detailed image of the infant universe. For years, it orbited the Sun, patiently scanning the sky, measuring those ancient microwaves with unprecedented sensitivity. In 2004, as astronomers and cosmologists began to analyze the first wave of WMAP data, they found something deeply strange. The map was, for the most part, exactly what the standard model had predicted. It was a beautiful random-looking pattern of slightly hotter, red, and slightly colder blue spots, a perfect confirmation of our cosmological theories. But there was one feature that stood out, one patch of the sky that didn't seem to fit the random pattern at all. In a region of the southern celestial hemisphere, centered in the constellation Eridanus, there was a single, enormous, cold spot. It wasn't just a little colder than average, it was significantly colder, with a temperature dip of about 70 microkelvins below the mean. While that sounds like a tiny amount, on the scale of the CMB's subtle fluctuations, it's a huge deviation, a statistical outlier of the highest order. The real problem, however, wasn't just its temperature, it was its sheer size. The CMB cold spot, as it was officially named, is immense. It spans a region of the sky about 5 degrees across. To put that in perspective, the full moon is only about half a degree wide. This single cold spot is 10 times wider than the full moon as seen from Earth. It is a vast, coherent structure in a map that is supposed to be purely random. This was a shocking discovery. The standard model of cosmology, which is built on the idea that the initial fluctuations were generated by random quantum processes during the inflationary epoch, simply does not allow for a single, non-random cold patch of this immense size. You can't just get a cold spot this big and this cold by chance, or at least it's incredibly unlikely. Scientists immediately began to calculate the statistical probability of such a feature appearing in a random Gaussian field like the CMB. The first reaction, as is always the case in science, was skepticism. Perhaps it was a mistake. Maybe there was some unknown error in the WMAP instrument or a flaw in the complex data processing that created the map. For years, this was a plausible explanation. But then came the European Space Agency's Planck satellite, launched in 2009. Planck was an even more powerful and sensitive instrument than WMAP, designed to map the CMB with the highest resolution yet. As its data began to come in, the entire cosmological community waited to see if the cold spot would disappear, exposed as a mere artifact. It didn't. The Planck data released in 2013 confirmed the existence of the cold spot beyond any doubt. It was there, just as WMAP had seen it, a giant, cold, anomalous bruise on the baby picture of our universe. The hole in the heavens was real. The easy explanations had been exhausted. The scientific community now had to face the uncomfortable fact that there was a major discrepancy between our best theory of the universe and what we were actually observing. The hunt for a real physical explanation was on. The hunt for an explanation. If the cold spot wasn't an error or a statistical fluke from the Big Bang itself, then it had to be caused by something else. Perhaps the CMB light in that direction started out normal, but something happened to it on its 13.8 billion-year journey to Earth. This led astronomers to investigate one of the most subtle and fascinating phenomena in cosmology, the integrated Sachs-Wolf (ISW) effect. To understand the ISW effect, you have to remember that the universe is not empty. It's filled with massive structures like galaxy clusters, which create deep gravitational wells, and it's also filled with vast voids, which are like shallow gravitational hills. According to Einstein's theory of general relativity, as a photon of light from the CMB travels through one of these structures, its energy is affected. When a photon falls into a gravitational well, like a supercluster, it gains energy, becoming slightly blue-shifted. As it climbs back out of the well, it has to expend that energy and it becomes red-shifted. In a static, non-expanding universe, these two effects would cancel each other out perfectly, and the photon would emerge with the same energy it had when it entered. But our universe is not static. We live in a universe whose expansion is accelerating, driven by a mysterious force we call dark energy. This acceleration adds a crucial twist to the photon's journey. Now, imagine a photon of CMB light approaching a colossal void. A void is a region with less matter than average, so it's like a gravitational hill. As the photon enters the void, it has to climb this hill, and it loses energy, becoming slightly colder and red-shifted. Now, while the photon is inside, traveling for hundreds of millions of years, the universe's accelerated expansion is stretching the void itself, making it larger and shallower. By the time the photon is ready to leave, the gravitational hill it needs to slide down on the other side is less steep than the one it climbed to get in. As a result, it doesn't gain back all the energy it lost upon entry. The net effect is that a photon of light that travels through a massive supervoid will emerge with slightly less energy than it started with. It will appear to us as infinitesimally colder than the photons from surrounding regions that did not pass through such a void. This is the integrated Sachs-Wolfe effect. It's a way for large-scale structures in the more recent universe to imprint a new secondary cold spot on the ancient light of the CMB. This provided a testable physical explanation for the cold spot. If this theory was correct, then there must be a truly colossal supervoid, an enormous region of space with a profound deficit of galaxies, lying in the same direction as the cold spot, somewhere between us and the CMB. The hunt was on to map the three-dimensional structure of the universe in the direction of Eridanus. This was a painstaking task. Astronomers used various telescopes to conduct deep galaxy surveys, measuring the redshifts of thousands of galaxies in that patch of sky to determine their distances and build up a 3D map. Early surveys were inconclusive, finding some smaller voids but nothing large enough to explain the effect. But in 2015, a team using data from the Pan-STARRS telescope in Hawaii and NASA's WISE satellite finally found it. By combining their data with earlier surveys, they uncovered a truly colossal structure. They had found the Eridanus supervoid. It is one of the largest structures ever discovered in the universe. It is a vast, nearly spherical region of space, centered about 3 billion light-years away, with a diameter of roughly 1.8 billion light-years. Inside this supervoid, the density of galaxies is significantly lower than the cosmic average. It is a true ocean of emptiness. The discovery was a triumph. It seemed to provide the perfect explanation for the cold spot. The void was real. But then came the final frustrating calculation. The supervoid was there, but was it super enough to create the entire cold spot? When cosmologists calculated the theoretical cooling effect that the Eridanus supervoid should produce via the integrated Sachs-Wolfe effect, the numbers didn't add up. The supervoid was massive, but it could only account for about 10 to 20% of the observed coldness of the cold spot. It was a contributor, but it was not the main cause. The vast majority of the anomaly, the deep, unusual cold, remained unexplained. The discovery of the supervoid had only deepened the mystery. The universe was hiding a secret, and it was going to take more than our standard theories to find it. Beyond the standard model, with the most plausible physical explanation falling short, the CMB cold spot remains one of the most significant and tantalizing anomalies in modern cosmology. It stands as a direct and persistent challenge to our standard model, forcing scientists to confront the limits of our knowledge and to consider possibilities that were once relegated to the fringes of theoretical physics. A 1 in 1,000 fluke. The simplest, and for many scientists, still the most likely explanation, is that the cold spot is just an incredible statistical fluke. The standard model predicts a random Gaussian distribution of temperature spots. While a spot this large and this cold is extremely unlikely is not the same as impossible. In a universe as vast as ours, with a sky full of random fluctuations, low probability events are bound to happen somewhere. Perhaps we just happen to live in a universe where the cosmic dice roll came up with this incredibly rare feature. It's the least exciting explanation, as it doesn't involve any new physics, but it's one that cannot be definitively ruled out. Many cosmologists are content to accept this, believing that as our statistics improve, the anomaly may appear less significant. A scar from the infant universe. A more exotic possibility is that the cold spot is not a product of the random quantum fluctuations of inflation, but a remnant of a different kind of event in the very early universe. This theory involves the idea of cosmic textures. Imagine what happens when water freezes into ice. As the crystals form and grow, they don't always line up perfectly, and defects or cracks can form in the ice. Some theories of physics suggest that the early universe went through similar phase transitions as it cooled after the Big Bang, where the fundamental forces of nature separated from each other. These transitions could have left behind topological defects in the fabric of space-time itself, structures like cosmic strings, domain walls, or cosmic textures. A cosmic texture would be a complex, knotted configuration of energy fields that would have long since untangled and decayed. However, as it untangled, it would have disturbed the surrounding space-time and could have left behind a large spherical cold spot on the CMB as its decaying signature. In this scenario, the cold spot is a fossil, a scar left over from one of the universe's most violent and formative moments. A bruise from another universe. The most mind-bending and spectacular explanation for the cold spot comes from the cutting edge of theoretical physics, the multiverse. According to some theories, like eternal inflation, our Big Bang was not a unique event. Instead, new bubble universes, each with potentially different laws of physics, could be constantly popping into existence in a larger megaverse, like bubbles forming in a pot of boiling water. Physicist Laura Mersini-Houghton and her colleagues have proposed a truly radical idea based on this concept. They suggest that the CMB cold spot could be a bruise on our universe, the tangible observational evidence of a collision with another bubble universe in the distant past. The theory is rooted in the principles of quantum mechanics. Before our universe inflated, it was a quantum object, and it would have been quantumly entangled with other nearby bubble universes that were forming at the same time. This entanglement would have created a gravitational pull between the universes before they began to inflate. This pull would have drawn matter away from a particular region of our universe, leaving it slightly emptier than the rest. When our universe then inflated, this initially small, empty patch would have been stretched to the enormous size of the cold spot. If this hypothesis is true, the implications are almost beyond comprehension. The cold spot would be the first ever piece of empirical evidence that other universes exist. It would be a shadow cast on our cosmic wall from a reality that lies beyond our own. A hint that our entire cosmos is just one island in an infinite archipelago. For now, the CMB cold spot and the Eridanus supervoid that lies within it remains one of the most profound and unsettling question marks written across the baby picture of our cosmos. Is it just a fantastically unlikely statistical fluke, a 1 in 1,000 chance that we just happen to see? Is it a sign of new physics we don't yet understand? A fossil from the universe's first frantic moments? Or is it something far grander, a glimpse of a reality that transcends our own universe? Whatever the answer, the hole in the heavens serves as a powerful and humbling reminder. It invites us to keep looking, to keep questioning, and to always be prepared for the universe to be far stranger, more complex and more magnificent than we can possibly imagine.